Hey guys, welcome back to my channel, and in today's chapter we are going to study drag. So this is the third chapter for your principles of flight, and I hope the previous two chapters you have understood it well. So let's begin. So what exactly is drag? Drag is the force that resists the forward motion of the aircraft. It's parallel and opposite to the flight path. So as I've said it in the previous video, I'll explain it again. So what is the flight path? It's the path followed by your aircraft. So if this is my aircraft, it's moving forward. So if you can see, this is drag, right? So this it's also parallel and opposite to the flight path. So what if I ask you what is the relation between drag and relative airflow? So I hope you remember. So relative airflow is always opposite to the flight path. So in this case, drag and relative airflow are parallel and same direction. And let's go ahead and study the formula for drag. The formula for drag is the same as the formula for lift. So from the previous video, I'm sure you know the formula for lift. It's half rho v square. Here instead of CL, it's going to be CD. So everything remains same. This is density of the air. This is dash. CD is the coefficient of drag. S is the surface area of your wings. Alright, I hope this makes sense. So when I talk about drag, it can be divided into two types of drag. The first one being the parasite drag, the second one being the induced drag. So the main difference between them is the parasite drag is independent of lift and induced drag is dependent on your lift. So when talking about parasite drag, it does not depend if you are creating lift or not, but induced drag, yeah, if you're creating lift, you're also gonna produce drag. Alright, so parasite drag can further be divided into three types of drag, which is skin friction, form, and interference. Let's go ahead and study them. So what exactly is skin friction drag? I'm gonna draw an aerofoil for you guys. So let's say this is an aerofoil. So let's say this is the airflow. It's moving like this, alright. So this is supposed to be a smooth flow of the air above. Now let's say that I'm gonna remove the airflow. Now let's say that the skin of the aircraft or the wing, it has some imperfections and it has some roughness, alright. So now in this case, when my air is flowing, this imperfection is gonna make it turbulent, right? The airflow is gonna lose its energy and it's gonna turn into an turbulent air, right? Makes sense? So this turbulent air, this is basically loss of lift if you see indirectly. So this type of drag is called skin friction drag. And how can you solve it? It's by polishing. If I polish the surface, let's see if I polish it out in a way, then I can manage to reduce the skin friction drag. Let's go to the next type of drag, which is form drag. Alright. So this is basically drag that is due to the frontal surface. So for example, let's say this is the aircraft, or let's go back here. Okay, so this is the aircraft, this is moving forward. So let's say if my landing gear is down, alright. So now my frontal area is increased, right? So this landing gear is of course gonna produce some drag. It's gonna slow the aircraft down. So this type of drag is called form drag. Also, there's one more way that you can look at form drag. So what's happening here? Let's say that's okay. Let's go back to our aerofoil. Alright, this is my aerofoil. So what's happening when the air, this is the stagnation point, right? I hope you remember stagnation point. So what's happening here, the velocity is 0 and your static pressure is the highest compared to your trailing edge. This is your leading edge, this is your trailing edge. So this condition when your pressure is highest at the is not highest but higher compared to your trailing edge, this is a characteristic of the form drag. I hope it makes sense. So yeah, so by the way, parasite drag, skin friction and form drag together make profile drag. This is an important thing that you must remember. So let's talk about interference drag. Let's go back to our aircraft over here. So do you see the wing here is joined to your fuselage, the engine here is joined to your wing, then your elevator here is joined to your fuselage, your rudder is joined to your fuselage. So this is so the basic definition for interference drag, the different airflows around the components, they combine with each other and give you interference drag. So I'll help you understand it better. So I'm gonna explain interference drag to you with an example so you never ever forget it. So for example, let's say this is a freeway and these are three lanes, 1, 2, 3. All right, makes sense. So here all the cars are moving fast. Let's say 100 kilometers per hour. This is the average speed of all the three lanes. And let's say this lane is connecting it to the freeway. It's comparatively slower. All right, let's say it's approx 50 kilometers per hour, which is almost half of it, right? And when it's merging with this, do you think the speed of this lane is still gonna be 100 kilometers per hour? Of course not, it's gonna reduce. This is due to the interference of traffic from this lane. Something similar is happening over here. Let's say this is your aircraft. This is the front view of your aircraft. Really sorry for my drawing. So this is your wing. So as you know, when you see from the side, this is your aerofoil. Your air is accelerated over here, right, on the aerofoil. So basically, the air is quite fast over here, and the air is comparatively slower over here. So when these together meet, they give a type of drag that is called interference drag. I hope it makes sense to you. So let's discuss the factors that affect parasite drag. So parasite drag is directly proportional to speed square, alright, and it's directly proportional to density and directly proportional to the surface area. So if you increase the surface area, what happens? It increases your form drag. So as you climb up, what happens to the density? It reduces. So there are less molecules that your aircraft has to get in contact with, and eventually your drag reduces. And when you increase your speed, you're gonna collide with these molecules faster, and this also increases your drag. Alright, I hope it makes sense. These are all the factors that parasite drag depends on. Now let's discuss about. Alright, yeah, I want to tell you one more thing. So snow, let's say it's snowing, and there's snow on your wing or on your fuselage. So this also increases your drag because this is going to disturb your airflow over your aerofoil, and therefore your drag increases. If there's snow, alright, I hope this makes sense. This is also an important point. Let's discuss about the second type of drag, which is induced drag. I hope you remember what I told you in the beginning of the video, that it is dependent on lift. So whenever your aircraft is producing lift, you're gonna produce induced drag too. Alright, so what exactly is induced drag? I'm gonna tell you. So as we discussed previously about weight turbulence, do you remember what weight turbulence is? So I hope you remember from the lift chapter that, let's say this is your aircraft from behind, this is your APU, your rudder, your wings. So when your aircraft is moving forward, and according to 3D flow of pressure, this is low pressure, this is high pressure, it's not only gonna create lift by moving this way, but it's also gonna seep towards from the side. Alright, so and when you're moving forward, it's gonna give you type of turbulence, it's called weight turbulence. Alright, so let's discuss what happens when you're actually reducing wingtip vortices. So let me draw an aerofoil over here. I'm gonna draw an aerofoil over here. I'm sorry, correct it. Alright. So when you're creating vortices, when your aircraft is creating vortices, what happens to your upwash and downwash is, let's say this is your upwash and downwash increase. I hope you remember from the previous video when I taught you ground effect. So upwash and downwash increase, and then your relative airflow changes to effective airflow. Alright, so let's say this is my increase of wash and downwash. Downwash has increased over here. Alright, so this was my relative airflow before. Due to this increase, this relative airflow is going to change into effective airflow. So this is my relative airflow and this is my effective airflow. And let me draw the chord line for you guys. So this is the leading edge, trailing edge, straight line, joining edge, leading edge, trailing edge, chord line. I know this is not a straight line, but just bear with me. I'm gonna show you something. Let me draw it with a blue line. Alright, so what exactly is angle of attack? It's the angle between your chord line and the relative airflow. So this is my origin angle of attack, but due to vortices, what has happened, my relative airflow has changed into effective airflow and my angle of attack has reduced. Do you see this? It has reduced this much. So if this was my lift before, now to maintain the same lift I have to pull back more. That is gonna increase my lift. So if this was my lift before, I have to pull back more, I have to increase my angle of attack more to compensate for the lift I have lost, which is gonna move my lift vector rearward, and this difference is basically what we call induced drag. Alright, I hope it makes sense. So let's discuss about the factors that affect lift. Alright, so yeah, so the first factor is gonna be speed, the speed of the aircraft. So basically, I'm gonna change the color over here. Yeah, so yeah, induced drag. Okay, so I wanted to remember something I taught you in the previous videos. So when talking about vortices, I told you something, right? When do you get the highest vortices? I gave you a memory item. It was HCS. See guys, if you remember this, there are a lot of questions based on this that you can easily solve. So what is HCS? Heavy, clean and slow. So what is clean? That means no flaps. So when your aircraft is heavy, clean and slow, it's gonna create the highest vortices. So indirectly, what does highest vortices mean? You're gonna create the highest induced drag, right? Makes sense. So if I increase my speed, right? If I increase my speed, what happens to my induced drag? It reduces. It reduces. So aspect ratio. Well, do you remember what aspect ratio is? So the aspect ratio is the span of your aircraft divided by the mean aerodynamic chord. Alright, so if I increase my aspect ratio, what happens to my induced drag? It reduces. Induced drag, it reduces. But I hope you remember in the previous videos I gave you a table to what happens if I increase the aspect ratio too much. Well, I'll write it down for you guys again. So if I increase my aspect ratio too much, first of all, my wing bending moments are gonna increase. Then my rate of roll is gonna reduce. My ground clearance during takeoff and landing reduces. Alright, so these three are actually important, so I hope you remember them. So of course there has to be some other way to reduce induced drag, right? We're gonna study it later. Let me explain this part of induced drag lift. Alright, I clear this and explain somewhere over here. Alright, so when talking about lift, what I actually mean over here is when I'm rolling, or let's say turning. So when I'm in a turn, what happens? When I'm in a turn, my lift is more than my weight. So let's say This is my aircraft, alright. Simple aircraft. This is my lift. This is my weight. Let's say this is a level flight. Everything is balanced, right? Your lift balances your weight. Now let's say I'm rolling. I'm sorry. So let's say I'm rolling. Again, this is the back view. So the rudder is gonna be like this. My wing is gonna be like this. My wing is gonna be like this. I hope it makes sense that I'm the rolling. So again, the weight of course is gonna act vertically downward. But now my lift has divided itself in two vectors. The first one is gonna be the one balancing the weight, which is the vertical component. This is the vertical component of lift, and there's gonna be a horizontal component. I hope you have studied this in your 11th and 12th grade. This is the horizontal component. So this horizontal component is basically pulling you towards the turn, inside of the turn, let's say. So do you remember which force pulls you inside when you're turning? Yeah, drum roll. Yeah, that's centripetal force. Alright, so centripetal force is the force that pulls you in a turn. So of course the weight has not changed of the aircraft in a turning, but now since the lift force has divided itself into two vectors, you have to increase the lift. So this vertical component balances your weight, or else you're gonna descend. And oh boy, you don't want to descend when you're turning, right? So what you do is you increase your angle of attack. So ultimately your lift is increased. But again, what happens when you increase your lift? Which drag is proportional to it? Induced drag. So your induced drag increases. I hope it makes sense to you. So now let's look at ways that you can reduce induced drag. So of course you discussed here that you could increase the aspect ratio, but I told you the disadvantages of it. So let's think of more practical ways you can do it, and I'm sure you have seen these ways. Alright, so to reduce, the first way is gonna be wing and plates. It's not very common nowadays. So if you see this wing, if I put a plate over here, I'm kind of restricting the sideways movement. Although there's gonna be some sort of sideways movement, but to a great extent it has been reduced. So the next way is gonna be tip tanks. So what happens? So okay, so let's say this is an aircraft. All right, front. Oh, sorry, it looks like a cat. Yeah, but okay. Anyway, so this is my aircraft wing. So where do you think the fuel is stored? Yeah, it's stored in the wing. The fuselage. So what happens if I store it over here? My induced drag is reduced. And also my wing bending moment is reduced. So that's like 2 plus 1. That's like a discount for you, right? It works for you. So the third way is gonna be winglets. And I'm sure you guys have seen this in aircrafts. In all the modern day airliners have this. So this winglet does the same thing as the wing and plate. It restricts the 3D motion of air around the wingtips. Now let's go to the next part, which is gonna be L by D ratio. So what basically is L by D ratio? It's the amount of lift generated compared to the drag generated. Because of course if you're generating lift, you're gonna generate drag. It goes hand in hand. Alright, so when talking about L by D, let's see the formula. It's half rho v square C L S, and what's drag? I told you the formula. It's half rho v square C D S, the coefficient of taking. So everything just cancels itself out, and it's basically the coefficient of lift and the coefficient of drag. So basically the L by D ratio, it occurs at a specific CL and angle of attack. If my aircraft is at this angle of attack and at this CL, my L by D is going to be the highest, and my drag, of course my drag is going to be at the lowest, that's why this ratio is the highest. This is going to be minimum, and the speed that refers to the L by D ratio is called the VMD. So what is VMD? It is the minimum drag speed. So if I make a graph for you guys over here, let's say on the x-axis I have my speed, on the y-axis I have my drag. Alright, let's talk about let's parasite drag. So what happens to parasite drag? I hope you remember parasite drag is proportional to speed square. Correct? Am I right? Yeah. So as my speed increases, my drag increases. This is, I'm gonna name it IP for short. That is, wait, I'll just write it down. This is parasite, right? So, and what about, let's say, what about induced? It's proportional to half v square. It's indirectly proportional to your speed. So as my speed increases, my drag is going to reduce. So alright, so this is the curve for induced drag. Even though also wait, I'm gonna okay, no, it's fine. Induced drag. So where do you think is the lowest drag? Alright, it's gonna be at this point, the point of intersection, where your this is the point where your L by D is maximum, and the speed, as I told you, it's a VMD. We call it VMD, minimum drag speed. So there's something about this point which I want to explain it to you. So what happens? So this point, first of all, these two lines are in contact over here. So what does it mean? It means your parasite drag and induced drag are equal. That's why this is their point of contact. And let's say if I increase my speed, okay, so let's say this is my VMD and I increase my speed. So what happens to my total drag? It increases. Okay, so I'm gonna draw the graph for total drag too. So this is gonna be the graph for total drag. So this is the lowest part, and then it increases over here. This is, oh, wait, I'm gonna draw it with blue. I'll write with blue. It makes sense. Oh, sorry. Alright, this is total drag, and let's go back to that. Yeah. So what happens if I increase my speed from VMD? So this is the highest one, right? For x-axis, I've increased my speed. So what happens to my total drag? That it has increased. But why has it increased? It's because of the increasing parasite drag. Because when you increase your speed, your parasite drag increases, right? So now let's say my speed has reduced from VMD. I'm flying slower. Again, if you see, this point is above this point, right? So my drag has again increased. But why this time? This is because of the increase in induced drag. HCS. You fly slow, you increase your induced drag. So I hope this graph makes sense to you. So alright, so let's say when you're flying and you lose your engines, alright, so you're no longer generating thrust, so you have no forward motion in the air, and therefore you're not generating any lift. So what do? You fly this speed, VMD. It's different for different aircraft. So for example, when I flew the Cessna 172, our minimum drag speed was 65 knots. So when you simulate an engine failure, you bring your speed to 65 knots by pitching up, which you'll learn. And this again, so what happens when I'm at 65 knots? I'm at my L by D ratio. So basically I'm making the most lift for the least amount of drag. So let's say my engine, I'm over here, I'm at 10,000 feet, my engine failed over here. So basically if I'm not at VMD, this is gonna be my path. Let's say this is the ground, this is gonna be my path. But if I'm at VMD, this would be my path. So I could glide, let's say I could glide more. This is how much I would glide more, just because I'm creating more lift and less drag at VMD. So I hope it makes sense. Alright, so now I'm gonna explain what is speed stability. Even though it's not that important for your DGCA exam, I'm gonna give you a quick brief explanation about it. So what is stability? It's the tendency of an aircraft to return back to its original state after a disturbing force acts on it. So what does this mean? So let's say my speed was 100 knots. Alright, this is my aircraft. It was 100 knots. Alright, and if I get a tailwind and it becomes 120 knots, if my aircraft is capable of coming back to 100 knots, this is called stability. Alright, and I'm gonna tell you the three types of stability. Alright, the first one is positive speed stability. The above example I gave you, where it came back to its original state, like from 120 it came back to 100, right? So this was an example for positive speed stability. The second is going to be neutral speed stability. So if it stayed at 120, there was no increase, no reduction, a constant speed of 120, then this would have been neutral speed stability. The third one is going to be negative speed stability. Let's say if it got increased to 120, but then it keeps increasing 130, 140, then this is called negative speed stability. I hope this makes sense and you guys enjoyed this chapter. This is a very interesting chapter, drag, and the next chapter is going to be even more interesting, stall. So I'll work on it and I'll get back to you with a good video.